Okay, on this video, we're going to talk about geometric series. This is another very special kind of infinite series, a very important one. Was saying that there's going to be about 11 tests to determine if a series converges or diverges. And many of those tests are actually based off the idea of a geometric series. So this is a real important one. Okay, so an example of a geometric series, I have 1/2 to the n, starting with 1 to infinity, which is generating the fractions 1/2, 1/4, 1/8, 1/16. And so what makes something a geometric series, just like for a sequence, if we're multiplying by the same number, the same constant each time to get from one term to the next, in this case it would be 1/2, that is geometric, and we're going to call that multiplier R. It stands for ratio. So to determine if this series converges or diverges, let's talk about, by converge we mean if we add up an infinite number of terms, do we get a finite number or not? So let's say we wanted to explore that. Let's say we wanted to find the sum of the first 10 terms just to see what happens if we're getting a big number or a small number. So there is a general formula for the sum of the first n terms of a geometric series, and it's a good one to know. So let's generalize here. We can apply it to this one when we're done here, but the sum of the first n terms, so for a geometric series, there's always a first term, and we're going to denote the first term as just a. How do we get to the next term? We multiply by our common ratio, r. And how do we get to the term after that? We multiply by r again, and so forth, right? Now, n, in this case, we're talking about how many terms we're finding the sum of. Notice by the time I get to ar cubed, there's actually 4 terms there. So the number of terms is 1 less than the power, which means if I wanted to add n terms, I would stop at r to the n minus 1. Okay, so this is what we're interested in. Now, one sneaky way to find a formula for S sub n is if I take this equation and multiply both sides by r. So the left side is r times S sub n. If I multiply a by r, I get ar, this one by r, and so forth. Now the term before here that I didn't write, multiplied by r, would have given me this, and ar to the n minus 1 times r would give me ar to the n. Now the reason we do that, if you subtract those two equations, we get a bunch of stuff canceling on the right side. On the left side, excuse me. On the left side, we just have f sub n minus r times s sub n. On the right side, all these terms cancel, leaving me with just a minus ar to the n. If you factor out an s sub n from the left side and factor out an a on the right side, then we can solve for s sub n, and we get a times 1 minus r to the n divided by 1 minus r. So this formula can be used to find the sum of the first n terms of any geometric series. So for our geometric series, our first term was 1/2, and so was our r value. So if I plug in 1/2 for a and for r, raise that to the 10th power, and do some simplifying, it turns out that the sum of the first 10 terms is 1023 over 1024, which is obviously very, very close to 1, right? And so it's a good indicator that, hey, when we add a bunch of these terms together, we're starting to get a fraction that's getting close to 1. But as we know, adding the first 10 terms together isn't the real test. We want to add an infinite number of terms. So we can still use this formula, though. If we take this formula and let n go to infinity, take the limit as n goes to infinity, then one thing to keep in mind here, if my r value was a fraction whose absolute value was less than 1, for example, like -2/3, and I raised that to the infinite power, that's like multiplying -2/3 times -2/3 times itself forever, because that fraction is less than 1, the absolute value of it, it's going to get smaller and smaller and smaller, and so your limit will be 0. So what do we learn from this? If we take our formula for S sub n, take the limit as n goes to infinity, as long as the absolute value of r, of my ratio, is less than 1, that term's going to go away, and it's going to leave me with a times 1 minus r. Remember what a is. It's the first term, right? First term in my series divided by 1 minus r. So what does that tell me? That tells me the sum is a number, which means the series would have to converge. And so this leads us to the geometric series test. If the absolute value of r in a geometric series is less than 1, then we know it converges, and we actually know the sum, what was on the previous page, would be a over 1 minus r, the first term over 1 minus r. What we also know is if the absolute value of r was greater than 1, then that sum would not have converged, right? R would have gone to infinity. So our geometric series will diverge if the absolute value of r is greater than 1. Okay. Coming back to my original series then, now we can look at this and we know our r value is 1/2. Since the absolute value of 1/2 is less than 1, the series converges and would have a sum of the first term, which was 1/2, over 1 minus 1/2, and that of course reduces to 1. Remember, we got a fraction pretty close to 1 when we did the sum of the first 10 terms. So this now confirms that the infinite sum would be 1. Okay. The geometric series test is an important one, and it's also usually fairly easy to spot, which is one nice thing. So this next example has what I call the classic look of a geometric series. You might have a number times a fraction to the nth power. That's a very characteristic geometric series. And you can confirm it's geometric if you wrote out some of the terms here. I have my n starting at 2. But nevertheless, each successive value of n, how am I getting from one term to the next? We're just multiplying by -2/3. So if your geometric series is written in this form, you can actually just read off your r value. That would be your r value. Since the absolute value of -2/3 is less than 1, I know my series converges by the geometric series test, and I can use my sum formula. Now again, just to emphasize, if you read the book, you might get confused about what they mean by a. A is the first term in the series. So in this case, my first term was 6 times -2/3 squared, and then divided by 1 minus r. If you do the math there, we'll get a sum of 8/5. Okay. Number 3 here. Another one has a very classic geometric form to it. And sure enough, my r value is sitting right there. It's -5/4. Because the absolute value of -5/4 is greater than 1, I automatically know that this series is going to diverge by the geometric series test. And that's it. I'm done, right? There is no sum for that one. Sometimes geometric series can be dressed up a little bit. This one doesn't have the classic form of a geometric series, but how do you spot it? If you see a bunch of numbers to the nth power on both the top and the bottom, or even just one place or the other, it's a good chance that it's geometric. One way to show it's geometric, I could either do some algebra and try to put it in a form that looks like your classic form, or if you just start writing out some terms. If n is 1, I get 2 cubed over 3 to the 0, and then 2 to the 5th over 3 to the 1st, 2 to the 7th over 3 squared. And you just ask yourself, well, what would I multiply to get from one term to the next? My numerator is getting bigger each time by 2 to the 2nd, right? And my denominator is just multiplying by 3. That gives me 4/3. Since the absolute value of 4/3 is greater than 1, we would know this series also diverges by the geometric series test. Okay. There's a bunch of application problems that involve geometric series. This is more of a medical one. Say that a 15 milligrams of a drug is taken each day, and makes sense, the body's going to remove some of the drug each day, right? Probably going to still be some left in your system. But let's just say, for the sake of argument, that each day you're going to take 15 milligrams of drug, and 80% of it is removed by the body each day. So how much drug will accumulate over a long period of time? Because you have to remember, by the time you take your next dose of 15 milligrams, you still have some left, right, from the previous dose. So if you start writing this out, this generates a geometric series. Your first dose is 15 milligrams. Your next dose is from the previous, I'm sorry, this would be your last dose. Let's say we were on whatever day. This is your last dose. You just took 15 milligrams. But how much would have been left in your body from the day before would have been 20% of the 15. From the day before that, 2 days before now, we would have had 15 times 0.2 twice, right? Squared, 0.2 squared. And then 3 days ago, you would have had 15 times 0.2 cubed. This amount, of course, is getting smaller over time, right? Because your body is removing it. And if you think about that, that's a geometric series with an R value of 0.2, which is less than 1. So we know it converges. And if we want to find the sum, we can use our sum formula, the first term over 1 minus R, and that gives me 18.75 milligrams. So that could be very useful. You can imagine if you're a doctor and you're prescribing medication to a patient, you think you're only prescribing a 15 milligram dose, but if this patient is taking that medicine every day, this will be sort of the long-term amount of drug that will be in the patient's body, right, over time. So that's important to know if you're a doctor or if you're a patient. Okay, here's another kind of creative one, but just involving the geometric series. Suppose you were to start at the origin, move up 10 units on the y-axis, turn right, and then go half of that distance, turn right again, go half of that distance, turn right again, half of that distance. So every time you turn right and you go half the distance you went before, okay? And so the question is, you can see from my picture, you are going to end up, it's going to kind of spiral around a certain point. So the question is, what point is this? Where is this going to end up? So the trick here is to think of your x and y coordinates separately. If we think about just our y value, you first go up 10 units, and then you go down 10 times a half squared, right? Because we would have multiplied by a half twice by the time we go down. And then the next term, you're going to go up by 10 times 1/2 to the 4th, and then down by 10 times 1/2 to the 6th. And you see you get a geometric series with an R value of -1/4, basically, -1/2 squared. Plugging that into your sum formula, we get a y coordinate of 8. And if you do the same thing for your x coordinate, you would first go, okay, this is just, you would first go over 10 times a half, which is 5, right? And then the next time you go left, you're really going -5 times a half squared, right? You would have multiplied this by a half squared, and you're going backwards. And then you're going to the right by 5 times a half to the 4th. Once again, it's a geometric series. Plugging it into the formula gives you an x coordinate of 4. So the spiral will end at the point 4, 8. Okay, in the next video, we're going to talk about the next test, the integral test.